Hey, it's Will. It is Saturday, February 15th. Now, I know my last video was also recorded on Saturday, February 15th. However, this is logical February 15th because I actually slept. And it's before midnight. So, two videos in the same day, but I don't consider that the same day. Those are different days in my book. All right, welcome to From Bronze to GM and miniKanren. This is episode 8. I'm feeling better today. Yesterday's video, if you watched it, I had read too much of the news. Oh, wow. Yeah. So today, less news and more. I was watching some of Vibe's Bronze to GM series for Zerg from 2021. That was fun, and I watched an Artosis cast, and I laddered. Quite a bit. I got cheesed out a little bit when I was laddering, but that's okay. I'll take those losses. That didn't bother me when I was losing those games. So, standard Protoss cannon rush into DTs, into Void Ray type stuff. Actually, I won one of those games. I think that player was a little upset. They certainly didn't GG. But I wasn't worried about winning or losing. So this is an important idea, I think. It's like I'm worried about improving. I'm not worried about winning. Okay? I'm worried about spreading creep and making sure my queens are injecting my hatcheries, and that I'm spending my larvae as quickly as possible. And I have good drone saturation. If I have too many drones on one base, that I Maynard those drones to another base, all that. Avoiding supply blocks, I'm really bad at that. I'm terrible at avoiding supply blocks. But I'm getting better at the other stuff, having queens just for spreading the creep. There were maybe 2 games I lost. There was one game in particular, and I got, why did I lose that game? It's like I didn't spread the creep. Didn't have any creep anywhere, and I wasn't hitting my injects and, standard stuff. So right now I'm kind of stuck at low platinum league or high gold. I'm still in low plat, but, I'm in danger of being demoted to high gold. It doesn't matter. What I'm trying to do is get my macro up to the point where I'm diamond macro. Okay. And then I can start adjusting things like scouting and have builds and be more reactive in terms of which counters I want to use. But right now I'm just like spreading creep, hitting injects, all those things. Like these are just fundamentals. I'm just trying to get those down. And so, if I get cheesed out, that's fine. Doesn't matter. GG, more skill, as White Raw would say. So that's fine. My last game, I ended on a pretty good game where the Terran at the end was like, whoa. I did the full Zerg swarm. So that was good. Day 9 has a saying that, up until a certain level, I think Day 9 is the one who said it. I've watched so much StarCraft but I'm pretty sure Day 9 I said that up until a fairly high level, if you're losing games, which you will, the problem is in your base, not your opponent's base, right? So it's like, well, how do I counter this sort of build? Or, my opponent's making a lot of this unit, or what do I do? The answer is, if you're Zerg, spread your creep and hit your injects and make sure your drone saturation is right and prioritize minerals over gas, avoid supply blocks and all that. That's what you do. It has nothing to do with your opponent until you're actually fairly high level. And then you could start worrying about what your opponent's doing. But, I'm still at the point where if a pro watched my play, they'd be like, you were supply blocked for an hour. I mean, for a minute, 15 seconds. And, you weren't injecting, you didn't have larvae, you were floating 3,000 minerals, you didn't throw down macro hatches, on and on and on. Your creep spread was terrible. That's why you lost. It has nothing to do with the particular strategy. If you actually concentrated on those fundamentals, you would, be in Masters League or High Diamond or something, right? Which, I mean, that I think is all true. So, yeah. So that was good. That was good. Yeah, and of course the analogy is to programming and research and all that. When we want to focus on these fundamentals. Now in StarCraft, some of these things would definitely be considered macro. Okay. But in some sense, this feels like, these like mechanical, these are like mechanical fundamentals, I would say, to some extent. And the mechanical stuff to me feels like in the last episode where we were talking about consing up a list or looking at the box and pointer, or like using car and cutter to traverse a tree structure, those sorts of things, where you just want your mechanics to be sound. Editing scheme code, being able to move around in the editor scheme code, making sure you're not making mistakes with parens, that's like avoiding the supply blocks. Okay, so if something that should take you 10 seconds takes you 40 minutes because you're trying to debug a recursive, like some program that's using recursive functions or relations or whatever, and your actual problem is your parens are wrong, or you didn't understand that you didn't have a proper list somewhere, or whatever it is. I've seen that over and over again, that people spend huge amounts of time, or a higher level thing is in like teaching the intro programming language course at Indiana. I noticed that almost invariably the students who had trouble later in the course, the real problem was they didn't understand the interpreter. They didn't understand the metacircular interpreter, the scheme and scheme. And so, yeah, of course, when you're doing complicated stuff with that interpreter, if you don't understand how the basic version works, then you're in trouble, right? So, my perspective became, okay, we need to make sure people really understand that first interpreter. So, yeah, same thing here. You don't want to build on a foundation of sand. Yeah. So, I'm feeling better today. Yesterday felt kind of grody. Ups and downs that come with the territory. So, that's the life of a researcher, right? I mean, it could be external things up and down, but like I could tell you also when your research isn't going well, or whatever it is, paper gets rejected, grant proposal gets rejected. I will I will not go into the recent news. Yeah. So, yeah. Oh yeah, and I got a nice thank you letter today in the mail. I rarely get personal letters, and thanked me from a student thanking me for something I did, some time, giving some time and ideas. So, yeah, that was nice. And I had a couple of fun comments on YouTube, and a couple of people joined the Discord, right? And I was just thinking about that. It's like, well, how should I feel about this in terms of, say a few people watch these videos, or a few people make comments or whatever. And I guess I was starting to think about the Brian Eno story and quotes about the Velvet Underground record and talking to Lou Reed about it, which I was able to track down. Supposedly Brian Eno and Lou Reed were talking about this and, having this conversation. And, Brian Eno said, or he was either paraphrasing Lou Reed or quoting him, or this came out of the conversation, whatever. But the claim was the Velvet Underground record only sold 30,000 copies, but everyone who got the record started a band. Now, I think those numbers may not be accurate and so forth, but I thought that was a great way to think about it. So, maybe a small number of people actually watch all these videos. I mean, maybe I make a ton of the videos, right? Who knows? I don't know. But the people who watch the videos, maybe they go off and do cool languages or cool work and, push constraint logic programming for further, or design a language they wanted to do, whatever it is. I also watched a video today from Drumeo. It's like on YouTube, but Drumeo video with Mike Portnoy from Dream Theater, which is like a progressive metal band, famous prog metal band. And it was him hearing Taylor Swift for the first time and then playing drums along with it without the drum track. It was interesting in a bunch of ways. So first of all, his first take is actually awesome. I think it sounds like much better than the official song. But the other part was, he's like, is this a popular song? It's like, yeah, it's got 3.3 billion views. He's like, oh, okay. And then he's like, okay, I don't listen to any popular music. And I understand that as well. And so when he found out it was Taylor Swift, I was like, I'm sorry, I didn't mean to mess up your song, but it's funny that this, this really good musician in a band that's famous for being like a musician's, band, right? Like a band musicians love. He had never heard any Taylor Swift songs. So he's like, oh, that's what it is. I heard my first Taylor Swift song recently too. Actually, I heard that one. I was playing the drums to it. So it reminds me of a Neil Stevenson story where he said that he was invited to give, serve on a panel or something like that about writing. And he was talking to an academic writer who was there. And she asked him, what do you do? And he says, well, I'm a writer. He said, no. I know that, but what do you do? And he was confused, and then finally realized, like, oh, so for someone from academia, they can't make a living, writing. They do something else. So they teach or whatever it is. Maybe they do editing, maybe they sell real estate on the side. Who knows? And his quote was something like, she hadn't heard of me because I was famous, right? And so Mike Portnoy hadn't heard the Taylor Swift song because it was famous. And that's kind of like me for Python and Java. It's like, oh yeah, Python. I used that 20 years ago. Java, I also used that 20 years ago. Not so much on the Python and the Java. I kind of haven't kept up with them because they're famous. I do stuff that's not famous. But hopefully it's like the Velvet Underground thing where there's kind of weird things. It's like the Captain Beefheart type thing. Yeah. Captain Beefheart's kind of a cautionary tale, though. So without the cult-like mistreatment of all the band members. Okay. So, previous ladder practice. So, well, this gives you something about my state of mind last night. Let someone whose work you admire has inspired you know please give specifics. So, I think that's important. Yeah. Practice consing up list and pair structures, drawing box and pointer diagrams, predicting where the REPL will print out dots for improper lists, etc. So I didn't give the cleanest explanation of all that stuff. I'll try to give maybe a cleaner explanation today. That yesterday wasn't my best probably. Okay. And then read up on lists, pairs, proper, improper lists, and the Scheme programming language, 4th edition. Read at least one Scheme paper. Okay, there you go. That's some ladder practice for you. So today, hopefully, you did some of that. So for today, we're going to concentrate on our micro and our macro. If you're not familiar with real-time strategy games like StarCraft, so the micro would be like moving units around. Macro would be like, building your economy and stuff like that. Day 9 has a very funny story about explaining micro, but I won't get into that. So our micro, which we started yesterday, was things like using cons and constructing pairs and proper lists, improper lists, quote, symbols, the empty list, car, cooter, null, question mark, that box and pointer diagrams, using all of those things. And we need to be able to use those. This is sort of like proper technique. This is kind of like for crack climbing. You need to know where to put your hands, where you put your feet, where do you put your thumb. Sometimes for a crack, you go thumb up. Sometimes you go thumbs down. Sometimes you have to stack your hands, all those sorts of things. Off with cracks require different techniques and so forth. So this is kind of our technique, kind of low-level technique part, which I'll call micro. And then macro. Okay, so first of all, this is continuing practice. Okay, so this is something that at some point I shouldn't have to remind you about, but you should be reading. I was happy to see some people like the History of Programming Languages books. Those are excellent. I mean, I reread Hopple 2 over and over and over again. So that's good. So keep reading. At this point, I'm not even particularly. I don't particularly care even what you're reading. As long as you're reading papers and papers involving, programming language stuff. And then, have a research notebook or be taking notes somehow electronically. It doesn't matter. It doesn't matter if it's on paper, if it's electronic, whatever. But, writing down what you're noticing and thinking about, writing about what you're reading, writing what you want to read. What are the interesting references that you've come across? If there's anything from this series that you find interesting, if there are things you don't know, if there are things you want to find out, if you're looking at languages that have cool features from like the Hopple series, okay, that you didn't know about, maybe write down there, write down those features and, what is it you might want to do? Okay. So if we, work our way up where we start doing some projects, what sort of project ideas are you starting to collect? Okay, all those things. And then Jason Heeman sent me a link to an archive preprint today that involves relational programming. So I figure maybe we could take a look at that. So that's the sort of macro that I do. All right, so these are all things that you have to keep doing on a continual basis at the macro level. So yeah, you need to be able to do this stuff in your sleep, the cons and the pairs, like that's like spreading creep or hitting your injects and not getting supply blocked. Like you just have to be able to do that. And then for the macro level stuff, there's like idea generation, thinking about, ideas, comparing different approaches, Think about what sort of projects you want to do, reading, all that. Okay, so yeah, those are things we can talk about, and then we'll figure out some ladder practice. Okay, so for the micro, let's investigate some of the things we talked about yesterday with conses and pairs and all that. In particular, what I really want to show you is how to practice these things. Okay, so how to practice. Yeah, or how to convert between different things. So let's start up Scheme here. So here's a game that I've played many times, and the game is I'm just going to construct some sort of nested list structure. There we go. Now in this case I'm using symbols, so I have a quoted list. It's a nested list. Okay, so a nested list is a tree. I have a quoted list involving symbols. I could put numbers in there. I could put hash T and hash F if I wanted to. I could mix them up. But you can see I've got nested lists. And so now the question is, how can I construct this list using cons, let's say, okay? Or another way to look at it is if I fully expanded the tree structure, where would all the dots be? Where are all the pairs? Okay, so this is a proper list on the outside. Notice there are no dots here, right? And you would see the dots up here too, because we're quoting this thing. But the main thing is the printed representation doesn't have any dots. Okay, so this is a proper list. Now we could have some dots up here, but what matters is the printed representation, if that has dots. So we have a proper list. This proper list has 1, 2, 3, 4 elements in it. Okay, so it's a list of length 4. Okay, so there's a function or procedure called length that's built in. So I can call length on the quoted list. So the quoted list, remember, quote of datum evaluates to the datum. So quote of that list evaluates the list. And because the list is a proper list, we can call length on it. We can't call length on something that's like just a pair. That's not a proper list. So if I call length on cons 3.4, there we go, exception in length, 3.4 is not a proper list. Now if I did cons 3 onto cons 4 onto quote empty list, so now that's I'm constructing a proper list 3.4, then it's fine, and so the length of that list is 2. Okay. So anyway, back to our list that we're playing with. So I just made up this list. Okay, could have come up with any other sort of structure. So now what I'm going to do is I'm going to cons up this list. And there are a couple different ways you could go about it, but I'll just show you one way. Remember, we want to understand like the pair structures, then what the dots mean, and all that in the box and pointer notation, all that. So here's what I'm going to do is I'm going to go ahead and fully expand this to have the dots. Okay, so here we have the list D. That's the same as the pair D.empty list. Okay, list D is the same as D.empty list. And if I evaluate the quote expression, so notice the quoted list, the outer list is still a proper list. And then here we have this D.empty list, but that prints as just like, the proper list D, because this is a proper list. Remember, a proper list is either the empty list or it's a pair whose cooter is a proper list. So that's an inductive definition. Okay, well, the empty list is an atom, a symbol is an atom. There's nothing more to be done for that pair. Okay. What about this list? Okay, so this is a list that contains a single element. The length of this outer list is 1. The single element is the empty list. But that's equivalent to this, okay, in terms of the pairs. And sure enough, we get the same printed representation. Okay, so now empty list is an atom, empty list is an atom. So this whole thing is a pair. We got a car, we got the cooter, we have the car, we got the cooter. Okay, great. What about the symbol A? The symbol A is an atom. There's nothing to be done there. What about BC? So this is a proper list of length 2. Okay, so what does that mean? It means that what this really is B dot proper list C. Okay, and we can see we have the same printed representation. And so we have the proper list C. What is that? That's the same as C dot empty list. Okay, same representation. You see how I'm filling in the dots? Okay, so here on the outside we have a list of length 4, a proper list of length 4. Now I can start, dotifying that as well. So the outer proper list is, well, that's the same as A dot and then that proper list. Okay. All right. And now we have a proper list of length 3. We had a proper list of length 4. Now we have a proper list of length 3. So we have the first element of the proper list, dot, and then we have a proper list containing these elements. Notice, by the way, how I'm able with my editor to, well, first of all, I can go forward. I can go like backward S expressions. I can go forward S expression, backward S expression. I can transpose S expressions and things like that, but I can also kind of move things around with the parens. If you use par edit, you can do, even fancier things. You don't have to do any of this. You could do it, just with a regular text editor without any support for parentheses. You should be able to do it. You should be able to do it on a blackboard, a whiteboard. You should be able to do it on a paper. Okay, I'm just showing you how my editor is set up, but you do want to make sure you can do it efficiently and effectively. However it's set up, but you should at some point be able to do all this without needing special editor support. But it's helpful to have it, right? So here I can see where the matching paren is. Okay, so that helps. And also I've got this mode set up where if I type a left paren, it types the right automatically. If I delete the left paren when it's empty, deletes the right paren. Okay, so now we have another proper list of length 2. So I can turn that into a dot, into a pair. Okay, so then we have the car and the cooter. All right, still prints the same representation. And now we have this final proper list of length 1, which is the same as that dot empty list. And we can see we have the same printed representation. So let's go up to the original printed representation. Here we go. And then here's what we get. So ABC, blah, blah, blah. Same here, same here. Okay. So this structure produces the same as what we had before. Okay, so that's the fully dotified, if you will, version. You can see why the Lispers didn't want to print out all the dots, by the way. Okay, this is pretty annoying. Now, what if we want to, turn this into uses of cons, right? Well, we can get rid of the quote, and every time we have a pair, like with the dot, Okay, so that means we have the car, the first part, and then the cutter, the second part. So we can remove that dot and add a cons, but we have to quote the symbol. Okay, so otherwise Scheme will think this is the variable a instead of the symbol a, and we will quote this list. Okay, there we go, same representation. Now I can do the same thing. I can get rid of that quote and say we're going to cons that quoted list to that quoted list. You always have two arguments to cons. Let me put this on a new line so you can see. Okay, so we got another cons. Okay, same printed representation. We just kind of work our way down. Now I can go inside of this list. I'm going to say, well, cons quote B. Notice how I'm pushing down the quote. Okay, I'm pushing down the quote. So instead of having an entire, quoted list here, or sorry, quoted pair, I'm just quoting that symbol now. Okay, and then here we have C dot empty list. Well, that's a cons a quote C to quote empty list. So we get rid of the dot, we add a cons, we make sure to quote empty list, quote the symbol, same representation. So I can keep going down here. So let's see here. Let me just make this a little easier to read. Okay. I'm doing control Control J? Okay. So notice we don't have any dots for this part. Okay, so now, well, we still have this quoted thing. We want to make sure that by the time we're done, the quotes are only on the symbols and they're only on the empty list. All right, so cons this, cons that, get rid of the dot to that. Cons always takes two arguments, get rid of the dot. There we go. Now we can go inside here, cons, get rid of the dot, and we have to quote these empty lists, run it, same printed representation. Okay. Yeah. And then here, we only have this thing left, so let's cons that to that. Okay, same representation. And now we just have one pair left. Cons quote D onto quote empty list. And we still have the same printed representation. Let me just make sure I'm being honest. Okay. Okay, you can see here's my original printed representation. Okay. And then, and then this is what I ended up with. Okay, so I was able to, take this quoted list, quoted tree structure, really, nested list structure, right here, and, fully expand the list, which is nested proper list in this case, to get all the dots, and then I'm able to replace all the dots with conses and then push the quotes in. Okay, so that's the sort of thing you should be able to do. And then, furthermore, let's see, last time we also, we looked at the box and pointer diagrams, right? So you should be able to draw a diagram that matches the structure. Okay. Now here it's kind of complicated. We got 1, 2, 3, 4, 5, 6, 7, 8 conses, which means we have 8 pairs. Okay, so we can double check. So for the fully expanded version, there should be 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. Sure enough, there are 8 dots and there are 8 conses. Okay, so that matches. So we would have 8 pairs. All right, so I guess we can do this. Let's just go ahead and do it. I'm not going to do this over and over again because it starts getting annoying, but all right. Let me see if I'm not super adept with this freeform tool, but let's copy over. So we could do it based on the conses. We could do it based on the dot version. The dot version is maybe a little easier. I don't know. Doesn't matter. You should be able to go by either. So, we have this outer pair. Now let's do the cons version. Okay. So here we have this outer cons, and we have the symbol A. Let's move this here. All right. So the car for that outer cons is the symbol A. So here we go. We're pointing to the symbol A. Whoops, lowercase. This is the hard part. Okay. So, pointing to the symbol A, the car of the first pair. And then the cutter is pointing to another cons pair. Okay, that's right. And let me just get rid of where these are pointing. Okay. We'll reuse what we have. All right. So, all right. So we have this pair, this outer pair from this cons. So we have the symbol A. So I'm showing the value, so you don't, the symbol, you don't have to quote the symbol. You only, the expression is quote A, and the value is the symbol A. So here we're looking at the values basically in memory. Okay. So we got symbol A for the car of that pair, and the cutter of the pair, the second thing in the cons, is another cons pair. Okay, so it's that thing right there. Okay, so we're pointing to a cons pair. That's right. Okay, so for that cons pair, there's a car part and a cutter part. So for that cons pair, this cons pair, the car is a pair, and so is the cutter. Okay, so both. Let me duplicate this. Both the car and the cutter are pointing to a pair. Okay. It's pointing to the whole pair, really. So, in any case, so for the pair it's pointing to for the car, okay, it's pointing. Okay, so the car of this pair is the symbol B. All right, so it's kind of like this. Except instead of an A, we have a B, and it's going to try to capitalize it probably. All right, there you go. And then the cutter of this pair, the second element, the second argument, the cons, is another pair. Great. Okay. Copy some arrows. It's easier to do on paper. All right. Pointing to a pair. Okay. Move these out of the way for now. Okay, so for this pair, so we have this pair here. Okay, so the car is C, the symbol C, and then the cutter of that pair is the empty list. Okay, or null. So once again, I have the car. It's going to point to the symbol C. Okay, and then the cutter of that pair is the empty list. And remember, we can indicate the empty list as nil, or whatever you want to call it, as a slash. You might also see this as like the ground symbol from electronics. Okay, that's another thing you might see. In any case, there we go. We got the nil. Okay, so far for that. Now we have this pair we have to worry about, which is this pair. It's the second argument to this cons. Okay, so that itself is another cons. Okay, another pair whose car and cdr are pairs. Okay, so let's see if we may reuse some of this. Oops. Okay. So we're pointing to different cons pairs here. All right. So the first cons pair is empty list and empty list. Okay, so this one right here is empty list and empty list. So let's see. Great. All right. And then the second pair, this cons, has the empty list as the cdr and the car is another pair. Okay. So the empty list there. Car is another pair. All right, and that is that car is a pair of the symbol D and the empty list. So here we have the symbol D. Oh. Whew. Okay. Now we got to check and make sure we got it right. All right, so it's a little, can we fit all this at once? Let's see if I can kind of move things around. All right, so we have cons of A, okay, to, okay, so the outer cons, the car is A, okay, and then the cdr is another cons pair, this thing right here, whose car is a pair and whose cdr is a pair. The car is this thing, which is a pair, whose car is the symbol B and whose cdr is another pair, whose car is the symbol C and whose cdr is the empty list. Okay, that looks right. And then here, okay, so now we're looking here. So we've got that cons pair whose car is this thing, which is a cons pair of the empty list of the empty list. Okay, so we got, looks like we're bowling and got two spares. And then the cdr is this other pair here. Okay, so the cons pair whose car is a cons pair, whose car is a D, symbol D, and whose cdr is the empty list. And then the overall cdr is the empty list. So I believe this is the correct representation of our list. Okay, so there you go. So you've got the printed, the nice pretty printed representation, and then you've got the cons version, fully expanded cons version. You've got the quoted version with all the dots. Now we can check, like, okay, so here's another way to check it. So here we have the outer list is a proper list of length 4 with, 4 elements. So we have A, the proper list BC, the proper list containing the empty list, and the proper list containing D. So the 4 elements for the outer proper list. Okay, so here is the outer proper list. So we have A, and then we have this proper list with B, C, and then the proper list containing the empty list, and then the proper list containing D. Okay, and then the outer list, that's a proper list because if we go across, the last cons pair has, ends with the empty list or the null. So remember, proper list is either the empty list or a pair whose cdr is a proper list. So we can kind of work backwards. So the empty list is a proper list, which means this pair, which has the empty list in the cdr position, is a proper list, which means that here we have a proper list because this pair has a cdr that's a proper list. That means here we have a proper list because we have a cdr, or we have a pair whose cdr is a proper list, and all the way back. Okay, so it's like we consed up the list. And the last thing we do is we cons the A onto the proper list. So anyway, there are different ways you can go about like consing things up. There's probably one or more official ways of doing it. My personal view is like it doesn't really matter as long as you can do it. You can do it accurately and accuracy is the main thing. Okay, so it's not even so much that you can do it ultra fast. Like the speed comes over time. It's just like, spreading your creep. And those are, or like those sorts of micro tasks, micro intensive tasks. Like what matters is that you remember to spread the keep or your creep, and that you have a macro cycle. So right, so it's a macro or micro. But you have a micro cycle where you're going through all your hatcheries, and you have the queens, maybe hotkeyed to spread the creep and all that like you're actually doing it. Okay. And then you can, and you're not forgetting, and you're doing it. It's like less important how fast you do it and more important that you do it. Here, it's a similar sort of thing. Like you'll get faster with more practice, but it matters that you can do it. Okay, so if you're twice as slow, if you're 3 times as slow, if you're 10 times as slow in the beginning, just concentrate on getting it right. Okay, and you can play this game where you look at the printed representation and all those sorts of things. And so I just picked some random structure, right? But you can play that game on your own, and I recommend you do it. You don't have to start it with something this complicated. I mean, another thing you could do is, like, here's another technique you can use, which is, all right, so say we want to build up that structure, right? We want to build up that structure using cons. Well, we can use like a substitution of variable type things, right? We could say, okay, that's great. So what do we really have here? We have, A, and then we have L1, L2, and L3, okay? In fact, we could even make that explicit. So we could, do a let binding. We could say L1. Actually, let's do it like E1. We have these elements, okay? So the first element is the symbol A, okay? And, we're going to end up with 4 elements. I don't know if you can hear like the snow plow. Okay, so we'll just quote the different parts of the list. Okay. And then, well, what do we end up with? So here's one way we could do it. E1, E2, E3, E4. Okay, so that should have the structure we want. That's right. Now, how do you build up that list? Okay, so for cons, you do it like this. You say we're going to cons E1 onto cons E2 onto cons E3 onto cons E4 onto the empty list. So this happens to be a proper list, so that's how you do it. And so we have the same structure. Okay, so the same printed representation. Okay, so now we have those conses. Those conses are done. Okay. Now we can go up into our let expression. So let gives names. You know, we've already seen let, right? So we're giving names locally to values. So okay, well here we have quote A, which is a quoted symbol. That's atomic. There's nothing to be done. But here we have another proper list. So we can get rid of the quote and we say we're going to cons, you know, I mean, you could do lists and all that stuff, but you know, at this point we can do it. Cons B, you know, quote B onto cons of quote C onto the empty list. Okay, so because we had a proper list there. All right, same printed representation. And then here we have another proper list. So we're going to cons the empty list onto the empty list. That's how you build that. Okay, same printed representation. And then here we have another proper list. It's a singleton list. Cons the symbol D onto the empty list. Same printed representation. So now what do we do? We start substituting in. Okay, so E1, right there. Get rid of that binding. Okay, and we can check this at every step. Check it every single step. Make sure the printed representation is right. If it's not, well, then you made a mistake. Go back. Okay, E2. Let's feed in for E2. Okay, let's get rid of the E2. Okay, same printed representation. Let's substitute in for E3. Let's get rid of the E3 binding. Same printed representation. Okay, substitute in for E4. And now I can get rid of the let entirely and just pull out the body of the let. Same printed representation. Okay, I can do it that way. So you can, you know, build up the pieces in terms of the proper list. So at some point, you know, you'll be able to kind of do this without as much mechanism. Okay, and in practice, you normally don't have to build up super complicated structures because you will be using things like let binding and passing arguments to procedures and, you know, pattern matching and quasi quotation and all sorts of stuff like that. But the point is, this is like an essential, you know, like micro thing. You have to be able to do this, and you have to be able to do it to a high enough level where you're not making mistakes all over the place. Okay, so notice I could do it different ways. I was able to do this a bunch of different ways. As far as I could tell, I didn't make any mistakes. You could say, well, you know, you're maybe not as fast as you could be, and certainly my typing skills are pretty bad. I've never been good at typing. But the point is, like, the way you waste a huge amount of time isn't because you're typing slow. It's because your parens are wrong. You've got the quote in the wrong place. You don't know how to make how to cons up the structure. You don't know how to use car and coulter, you know, all that sort of thing. So, yeah. Now, we could also talk about car and coulter with that structure, right? So, you know, remember, with a cons pair, the first part of the pair is the car, and the second part of the pair is the coulter. So we could, you know, like say we wanted to get to this B, we could see, okay, so we have the pair, okay, so we have to take the coulter of the pair, follow that arrow. So we have to take the coulter, then we have to take the car, and then we take the car. So coulter, car, car. All right, let's try it. Coulter of the car, of the car, and I'm saying that should give us the symbol B. See if that works. Oh, I've got it backwards. Yeah. The cutter. So here I made a mistake. So the cutter, we have to do that first. So that call has to come innermost to our list. Okay. So the cutter happens first, and then the car, and then the car. Okay. All right. But you can see we have a B. And if we wanted to, we could do our shorthand that we saw, right? CAADR, cadder. I don't know how to say that. So if we wanted, we could do that, and then we get our B, all right? So yeah, so I made a mistake there because I had it backwards, right? So even though, so we have to take the cutter first, but because we have chained or nested procedure calls, that means, if we want to take the car of the cutter, then the cutter, that means the cutter is coming on the inside of my list. Okay, so this would follow the cutter pointer and then the car pointer. So this was like, we're going to follow the cutter pointer and then the car pointer, and this would give us that whole pair. So yeah, so we're doing the car of that. Okay, so I had that backwards. So yeah, that's fine. Okay, so but you can see how you could follow this around, right? So if you had to get the C, okay, so see if I can do it this time without making a mistake. So we're going to take the cutter, and then we have to take the cutter, the cutter, the car, the cutter, the car to get C. Cutter, car, cutter, car. Okay. So the cutter comes first, and then the car, and then the cutter, and then the car. So you have to chain it up backwards. All right. And that should get us to the C. So let's grab our list. Here we go. Here's the list. Yep, there we go. We got a C. And if we want to, we can compress it. That's the CADADR. Okay, well, yeah. That should be, that's 4 letters in the middle, 4 A's and D's. So that should be defined. Okay. There we go. C. If we want to have any more letters in the middle, we'd have to define our own. But at this point, it's starting to get a little ridiculous. But you could see how we could just follow those pointers and navigate through. You can also just like do it a little bit at a time. So, so here's, if we have, well, let's just give a name to this. I'm getting tired of pasting in the console. So I could say define, T. This is my tree. Okay, so here's our tree. And so we take the cutter of tree. Let's try to get the C, right? Okay, and then we need to take the car because we have a proper list. We need the first element of that. Okay, and then we need to take the cutter of that. And then we need to take the car of that. Okay, there's our C. Yeah, that's it. Okay. I'm sure hotshots have got all sorts of fancier ways of doing this. You probably can come up with better ways than I'm showing. It doesn't matter. It just matters that you can do it. And it doesn't matter you're super fast, actually, to begin with. You will get faster with experience, but it matters you can do it. And if you do make a mistake, you should be able to catch it right away and fix it. Okay. You don't want to fumble around with this. Yeah, so this is just like a key thing you need to know how to do. It needs to be second nature. Okay, so you're not fumbling around with it. It says it's just like, in a real-time strategy game, if you can't manage your base, when everything is going well, like how are you going to manage your base in the middle of some melee or something, right? Everything's going to fall apart. So if you can't cons up a tree structure or get the parts of it using Karen-Kutter, just like this, right? It's this little simple exercise. Well, how are you going to write recursive functions and recursive relations and all that when you have, quasi-quoted things and you're doing pattern matching and you have to cons up stuff and you've got recursions going on and all that? You're going to have a bad time, and it's going to be like the day 9 quote. Like, the problem's not going to be because you're trying to do something fancy. The problem is going to be because you can't cons up a list. Okay, so a very important skill to just be able to make sure you can do it. Okay, so it's bread and butter, meat and potatoes, however you want to say it. Okay, I guess there's like vegetarian and vegan versions of everything. Like in the Reason Schemer, all those foods are vegetarian. Yeah. So that's our little micro practice. So let's, first of all, I'll save this. Okay. And then if we go here, so the ladder practice, the micro part, practice consing up various patterns, various tree, Karen-Kutter to access symbols, access values in the const up tree, drawing box and pointer, diagrams, and predicting what the printed representation of a cons expression will look like. Okay, so this is similar, basically what I gave you yesterday, except we're just going to focus more on the practice. All right. If you think you already know how to do this, I challenge you to try doing some complicated structures and see how quickly you can do it. Okay, so that's something I would do, is that trying to keep very, very high level accuracy, just trying to speed it up. Try to speed it up, and while still not letting the accuracy slip. Okay, so can you do it as fast as you can type? Okay, if you can do it as fast as you can type over and over again with 100% accuracy, great. Okay, then you're good to go. If you're fumbling around, it's also a good thing where it's like, well, you can decide if your text editor is set up in a way you like, that sort of thing, right? So anyway, you just should be able to do that. Okay. And we're also going to be, looking at writing little recursive procedures and those sorts of things. We're going to be looking at different types of quotation, like quasi-quotation, using that, unquotation, pattern matching, but at some level, everything is based on this idea that we have pairs, and you have to understand that, and you have to be able to manipulate them. You have to be able to take cars and kutters. Even if we're pattern matching, it's sort of at the end of the day, there's still cars and kutters. So that's your micro practice, okay? Now, for the macro, you should be reading. You should be reading research papers. You could be looking at history of programming languages. You could be looking at structure, interpretation, computer programming if you want. You could be reading parts of the Scheme programming language, 4th edition. You could be reading the R6RS report, for example. These are things that you should be practicing, okay? I gave you some reading last time to look at the explanation of pairs and lists in the scheme programming language and R6RS. Yeah. So, and also you should be writing down ideas. Okay. Okay, so your ladder practice is write down ideas and observations, what you're reading, what you want to read, questions and potential research projects, all those things. That's a regular practice, okay? It's a regular practice. So just get in the habit of doing that, please. All right, and then let's look at an authentic practice. So Jason, sent me this paper. So let's take a look at it. Oh yeah, so let me save this PDF. Save it later. Okay. So this is a paper that's on Archive. If you're not familiar with Archive, it's a preprint server. Okay, so people can post the research. This is not considered publication. This is not a journal or whatever, but often people, before they submit to a journal or sort of their own personal copy or whatever, they'll upload it. So it's a chance to see what are called preprints of research and for research to be disseminated. And it's really changed the way science is done and research is done. So in biology, there's bioRxiv, for example. So posting things to bioRxiv is now very standard. Yeah. And, more often, like I think I already mentioned this, for things like workshops, maybe instead of having a proceedings that's say a university technical report, maybe people just post the papers on Archive now. Okay, so here's a paper from Archive, and you can see there's like, oh yeah, here it is. Let's see, can I rotate that? So I'll rotate right. You can see the Archive identifier is like version 1. Okay. February 12th, 2025. Today is February 16th, so this is pretty much hot off the press. All right. On constructing finite automata by relational programming. Oh, relational programming, finite automata, two things close to my heart. All right, let's look at the abstract. Okay, well, actually, there's some, the authors have these little superscripts. Usually these are either acknowledgments or email addresses or affiliations or whatever. So let's go down. Wait. All right, so I'm a little confused already. So usually there'd be here like a footer or like footnotes for 1 and 2. Yeah, so I'm confused. Yeah, I'm not sure where those are. Let's just see. Are there? Okay, so even in the heading, it's got 1 and 2. Okay, so is there a 1 and 2? There doesn't seem to be a hyperlink there. Now here's a footnote 1, but that doesn't seem to be an author affiliation. So that's a little unusual. I think that's maybe an oversight. I don't know. Maybe it refers to acknowledgments. Let's look at the acknowledgments. I'm not seeing a 1 or 2. Okay. Well, I'm confused by that. Let's see if we can. Let's go to the archive. Here's the archive website. Thank you, Cornell University. We could view the text source, I guess. Let's view PDF. That doesn't look like a link. Could view the text source, download it, tar.gz. Okay, open it in Text Shop. We could open it. Font small. Let me just open in Emacs. This is a little bit of an aside, probably, but I'm just a little curious about that. What's that supposed to be? Okay. So this is the address. So you could see the one is Akita International University, Japan, University of Waterloo, Canada. Okay. And then it's got the email addresses. So for whatever reason, those didn't end up showing up in the PDF the way it was typeset. At least I didn't see it. Yeah. So I'm not sure. Maybe something about the style, something about the way it's typeset. Okay. Well, in any case, now we know the affiliations. If if that's of importance or whatever. Now let's go on to the abstract. And we consider ways to construct a transducer for a given set of input word to output symbol pairs. This is motivated by the need for representing game-playing programs in a low-level mathematical format that can be analyzed by algebraic tools. This is different from the classical application of finite state automata. Thus, the usual optimization techniques are not directly applicable. Therefore, we use relational programming tools to find minimal transducers, realizing a given set of input-output pairs. This sounds like some sort of synthesis problem and maybe like parsimony or smallest. Okay, so now one question. So if I'm looking at a paper like this, so one question is relational programming. Okay, that could mean different things. So that could have something to do with, say, relational databases, or there's something called step indexed relations that are used in programming languages. There could be all sorts of things. I mean, relations come up in math all over all the time. From the abstract, I'm not sure. Now, I happen to know this probably has to do with my relational programming or the type of relational programming my collaborators and I do. But often it's the case where I can't tell from the title. And in this case, maybe I can't tell from the abstract. So I can go on and read the introduction. Okay. Or at least skim it. So, one thing I might do, so this is a pretty short paper. It's like 9 pages. One thing I might do is just kind of go through, just skim the paper and see things like what are the figures and what are examples. Okay, this looks like some sort of like finite state machine diagram, relational programming solution. Okay, so I'm looking for like code and figures or, mentions of things like miniKanren or Prolog or answer set programming or whatever. I'm not seeing anything like that so far, but here we go. Here we see logic variables. Okay. And then we have palindromes. Okay. I'm quite familiar with palindromes with miniKanren stuff. Okay, we keep going. Word classification. All right. More figures, more state machine or transducers. Okay. All right, so here we have some sort of benchmark, it looks like. All right. Conclusion and future work. So I haven't seen any code. We've got these transducer figures. So let's go ahead and look at the references. So this is something I often do, is jump fairly quickly to the references. And so if you look at the references, this can be helpful for a few reasons. So one is maybe there's something you want to read. Maybe there's something that looks interesting or relevant. And then secondly, if the paper is written in a reasonable style, like you can tell from the references usually what it's about. So here's a Rich Hickey, A History of Closure. Okay, cool. Here's Hopcraft and Ullman, Introduction to Automata Theory, Languages and Computation. I had that book when I was doing undergrad CS. And David Silver et al., Mastering the Game of Go with Deep Neural Networks and Tree Search. Okay, so AlphaGo. John von Neumann. I don't know what that is because I don't speak German. Yeah. Okay, 1928. Alfred Aho and Margaret Korosik. Efficient string matching. Okay. Okay, this one I recognize. William Byrd, Relational Programming, miniKanren, Techniques, Applications, and Implementations, PhD thesis, Indiana University, 2009. Yeah. Okay, so now we're getting into the authors. Computational Semigroup Theory Software System Written in Clojure. Okay, so here's some Clojure. I don't know if it's pronounced Kaigen or what. And here we have a GitHub repo, so we can look at that. Okay. And then we have the authors and other people. Transformation semigroups as constructive dynamical spaces. Okay, so where is this? So here we have a GitHub repo. Here we have a paper. Okay. And Fernando, I don't know editors, digital ecosystems. Okay. So from 2010. All right, so this paper is from a while ago, actually. Okay. Whereas the repo is from 2023. All right, so here's the Reason Schemer. It's the first edition cited. John Rhodes, Application of Automata Theory and Algebra via the Mathematical Theory of Complexity to Biology, Physics, Psychology, Philosophy, and Games. That sounds interesting. Original version, UC Berkeley Mathematical Library, 1971. So it sounds like it's a reprint. Okay. All right. Oh, okay. Here it is. I missed it. So, LaTeX put these all the way at the end of the paper, below the references. Okay. I guess that's fine. Usually I see that on the first page. Okay, so it did get typeset. I was a little confused by that. And then here we have acknowledgments. Okay, so this project was funded by a grant by the Japan Society for Promotion of Science, titled On Progressing Human Understanding in the Shadow of Superhuman Deep Learning Artificial Intelligence Entities. Okay, interesting. And then National Sciences and Engineering Research Council of Canada. Okay, so there are some grants here that were funding this work. Okay, so now that I've looked at that, so clearly this is related to miniKanren and to probably core logic and Clojure. And now we can go ahead and try to make more sense of it. So what is this about? Let's look at the intro. A fully calculated game tree, okay, so it sounds like search over a game tree, is a perfect solution for a deterministic two-player game of complete information, which StarCraft is not. Not perfect information. Working back from the leaves, one minimizes the maximum payoff the opponent can achieve using minimax strategy, as demonstrated by von Neumann and okay, so this is minimax. Okay, standard approach to game-based tree search. However, the tree may not be the most suitable representation for all purposes. Here, we're interested in the algebraic study of games. Okay, so here, we're seeing these different references, 10 and 8. Now, my personal preferred style is where there's like author year instead of like, okay, so what is 8? I don't know. But as long as I can click on it, it's not such a big deal. John Rhodes, okay. And I don't know the John Rhodes stuff. Okay, how do I go back? Oh. How annoying. I know. Go. Previous item. Go back. No, is there not a button for that? Tools. Oh. Show inspector. All right. Well, that's a little annoying. I'm sure there's some way to have a button do it. Therefore, we prefer a finite state automaton representation, as those define canonically associated transformation semigroups. These, in turn can be studied by the hierarchical decomposition tools. The question naturally arises, how can we create finite state automata for playing games? Okay, well, this is interesting, and I'm interested in game playing and things like AlphaGo. Formalizing lossless machine learning problem. Okay, so there's some machine learning stuff here. Relational programming solution. Okay, implementation. Here we go. We use the miniKanren family of programming languages for relational programming. It has a minimalistic approach famously described by only 2 pages of source code. The simplicity also means it's easy to implement, so forth. Okay, core logic, closure, all this sort of stuff that we're familiar with. Or you will be familiar with if you're not familiar with it now. Logic variable consideration is set up. Okay, so this is like how the problem is going to be described in miniKanren. Looks like computational complexity. Okay, so I guess if we want to see the code, we're going to have to go to the repo. Let's go to the repo. Yeah. Okay, so 10 years ago and 3 months ago. Okay, 2 months ago. All right. Computational semigroup theory system software system written in Clojure. There we go. To shadow other computer algebra packages in semigroup theory. To serve as a clean room implementation recomputation tool. Interesting. So semigroup packages for the gap computer algebra. All right, so this is like all computer algebra stuff, which I know a little bit about, but not a whole lot. Backtrack search for relational morphisms. Again, origin in Japanese. Okay, so that's a Japanese word. I have not gotten to that in my Japanese studies yet. Come back, notation grammar. All right, cool. So, my initial assessment is this is clearly related to miniKanren. It's using Clojure core logic. There's a repo that's been around for quite a while. It has to do with abstract algebra and computer algebra systems, and seems to be some relation to machine learning and finite state transducers. Yeah. Okay. So I think at this point, I would probably do a closer skim of this and, and then I'll probably just go through and try to read it. And I'll probably get stuck at some point or confused. And then, I like Richard Feynman's advice is that if you're reading a paper and you get stuck, just keep reading, like keep going. Okay. Don't stop. Keep reading to the end and then reread the paper again, because often by reading later, you'll fill in some of the gaps or things that you weren't sure of. So now I use another strategy, which is maybe related, which is if I'm stuck on a paper, I'll often read it backwards. If I get stuck, I'll start with like, okay, well, you can't hide your references or the conclusion, right? I'll just kind of work backwards. Conclusion and future work. So let's just read this. We applied relational programming to the problem of constructing minimal transducers for a given set of pairs consisting of input words and their corresponding output values. We compared the method with the classical method, minimizing in the trie or tree. Technically, this is pronounced tree, T-R-I-E, for retrieve, but a lot of people call it trie, so you don't get confused with the regular tree structure. In summary, relational method produces a truly minimal transducer, but is computationally intensive and does not scale well. In contrast, the traditional method does not yield a minimal transducer. This does not contradict the fundamental theorem about the unique minimal automata for any deterministic finite state automata, since we have flexibility in defining the output function, and we do not care about the values associated with the input words. Okay, there are at least two different ways for trying to further advance solution to this non-statistical machine learning problem: developing an incremental construction algorithm using relational programming, adopting more advanced classical approaches. Okay, I'd be curious about this incremental version. And I wonder if things like tabling could help. So I guess, I'm not shocked that their approach, maybe they ran into problems with scalability. I guess one question is, for their encoding of this problem in core logic, how are they running into some of the classic issues with sort of miniKanren search, or how efficient is their encoding, and how efficient is like the search and things like that for this particular problem. So they are getting the minimal transducers. So that seems to be important. So, but it sounds like it's too expensive. So, and I'm also curious for this sort of problem if something like answer set programming or, is this something like an SMT solver would do well, or is this something like Datalog would work well for? I'm not sure. Okay, well, that is kind of my quick overview, and I think I'll give this a closer reading. When I read a paper like this more closely, I tend to print it out and then mark it up, and by the time I'm done with it, it's got like completely covered with my chicken scratch notes. I don't particularly like reading on the computer. I like to, it's hard for me to do a really in-depth reading of something like this without marking up everything. But so that is an example of looking at a recent archive paper. And it has to do with miniKanren. And I know a little bit about the problem domain, but I'm not an expert. So I'm just kind of curious about what sort of issues they're running into, and with whether or not things like tabling might help. or bottom-up evaluation, stuff like that. Okay. So that's our our macro. Yeah. Just think if there's anything else for ladder practice that'd be good. I think for this time, you've got enough to just make sure that you can practice the the kanzing and all that. If you're an old hand at that and you know that backwards and forwards, then I'd say concentrate on your idea notebook. If you're not an old hand at kanzing things up and all that, please practice, because that will be essential. That's an essential skill, and you want to not get tripped up by it. Okay, because when you're trying to, it's actually, this is very much like StarCraft. If you're writing a program that's tricky, you really, your fundamentals will keep you keep you aligned and keep you safe and keep you pointing in the right direction and not spending hours debugging something. So you want to make sure that you can cons things up and you understand the pairs and the dotted, like the dots and the printed representation. You know what a proper list is, and you can do the box and pointer notation, go back and forth between different representations. Very important that you be able to do that for scheme. Okay. All right. I think that's enough for today. I think that's good. Alrighty. Have a good one. Hope to talk to you soon. Bye-bye.